Okay, so all in all, this is kind of our toolkit for resistances. Anytime you want to compute, just get a handle on the problem, go to something like this, and it really gets you a head start. Right? So the last thing we can do, let's see, this is the last thing. So what we'll do is just go through a really quick example of how to apply our resistances in a resistance network, and then we'll wrap up. Okay, so let's go back to our two material plane wall situation. We've got two materials, high conductivity, low conductivity. Over here we have, let's see what we have. So we have convection. So over here we have convection. And then at this boundary, and then between that we have conduction. Here we have a contact resistance. Again, we have conduction. And here we have convection. All right, so altogether we have, let's see, 1, 2, 3, 4, 5 resistances that we're dealing with. All the resistances are in series. And if you remember circuits, you can model electrical resistances in parallel or series, depending on the actual physical configuration. Same idea here, you can do both, right? Everything here is in series. Heat that's flowing from 1 must go through the convective resistance to get to 2, and so on, all the way out. Okay, so when we draw this out, we're just going to have a big series of resistances. So I'm going to do that over here. So we'll start up at the top. We're going to say up here, this is T. I'll just call it TH because I don't know infinity a bunch of times. The TH. Okay, then we have a resistance. This resistance is our convection, and this is at surface A. Okay, then we have another temperature, right? These nodes represent places where you could evaluate temperature using this relatively simple model. Okay, so then we have another resistance due to conduction, so we'll call that our conduction. Okay, and then we have our contact resistance. We have conduction in B, and then we have convection on the B side. Okay, and then down here, this is what TC. All right. So what I want to do is just really quickly evaluate, the values of the resistances here, and we can get a sense of what the temperature profile is going to look like. Okay, so for convection A, right, what was our rate equation? That's equal to 1 over H bar, let's see what we call H bar H, times the area available to it. The area, again, is not given to us, so let's just do this on a per unit area basis. Our area is 1 meter squared. Okay, so then we just have 1 over HH, well, that's 1 over 10, so that's 0.1. That's our resistance. And what are the units on this? Well, the units would have to be consistent with Q dot equals TH minus TC over R. All right, so the units on this have to be units of Kelvin per watt. All right, Kelvin per watt. And actually, thinking about the units kind of makes sense, right? If you have a resistance, this is telling you how many degrees Kelvin you need across this resistance to achieve 1 watt of heat transfer. All right, so 0.1. Okay, carrying on, then we have conduction. Now we have L over Ka times A. So it's just L, which is 0.1 over Ka. And these, let's see, I'll just write them out. I have them written down already. Wherever they went. Okay, 0.01, right? Kelvin per watt. Our contact resistance is R double prime C over A. So it's just R double prime C, so that's 0.001 Kelvin per watt. B was 0.1. And let's see, the convection was 0.01 Kelvin per watt. So we'll just highlight these so we can see them. 0, 0, this one. Okay, so we have all 5 of our values, right? So now we can just look at this and we can say, if I want to know what should I include in my model? If I'm going to go to the trouble of now developing a more detailed model, maybe this is like something you actually care about, some process you actually care about. What is important here? Like what's dictating the heat flow through this thing? And where am I going to find most of the temperature drop in the model? Yeah, Matthew? Did I switch? Maybe I switched it around. Okay. Yeah, it's possible I flipped them around, but it's okay. No, okay, yeah, I'm okay. So, great, we want to look at this and just say what's important. Okay, looking at this, what's important? Well, for me, convection and conduction B, right? Convection A and conduction B, those by far have the largest resistance. So when I look at the temperature profile here, I will find that that's where my temperature drop is. Right? That's what's dictating heat transfer from the hot to the cold. I could pretty much care less what RC is, right? 0.001, it's 2 orders of magnitude smaller than the other resistance. So if I'm spending time building a model, I'm just going to ignore that. I've proved here that it's really not that important. Okay. And in fact, if we were to try to sketch this out, we'll do like this. If I sketch this out, I have temperature as a function of position here, call that X. I can pretty accurately sketch out what I think this is going to look like without even doing any further analysis than this. Okay, so if I draw my temperature profile as a function of position, or let's say up here we've got 300 Kelvin, down here is 100 Kelvin. My sketch as a function of position might look like, okay, I've got, right, most of the temperature drop has to be convection A and conduction B. So I'm going to start up here, and I'm going to have a big temperature drop here. There's a relatively big temperature drop. But across A, it's pretty small. The contact resistance is basically nothing. There's another drop across the conduction that's pretty big. And then I have a smaller drop across the last convection. And so if I sketch this out, it might look something like this, right? Here's my convection temperature drop. Here's my conduction temperature drop. My other conduction temperature drop. And my last convection, right? By the way, I just kind of draw it as a curve because that's what the actual profile looks like when you get to the boundary layer. So this is a reasonably accurate assessment of the temperature in this body, and all I've done is calculated really trivial things. Sometimes this can be good enough, right? If you're just trying to prove a point to your manager and say, look, this is important or not, like this could be good enough. Sometimes if it's just a tool to guide the next step in what you're actually doing.